Today's topic is identifying potential for performance improvement. And in today's session, we'll look at ways of identifying opportunities for improved lagging performance on both new conveyors during the design stage and also on existing conveyors. By improved performance, I'm referring to improving the performance of the pulley lagging and conveyor belt interaction. To start with, let's look at drive pulleys on conveyors in the design stage. Here we'll be looking at things like power transfer, localized slippage, the inherent cyclic shear stresses that both the lagging and the belt splices have to deal with. We'll be looking also at how this relates to the fatigue life of each of these components. In course 2, we discussed using the lagging select software tool to identify lagging failure root causes and to assist in evaluating options for addressing these root causes. But there's another way that this engineering tool can be used, and that is to evaluate different lagging types and designs on drive pulleys by comparing a number of key performance criteria, specifically localized slippage, fatigue failure, in particular in 3 key areas of the lagging, actually 4 key areas of the lagging. You can see here we have the pulley shell interface, the tread root, which is at the base of the grooves on the lagging, the contact face, and the tile bond surface. Additionally, the tool allows us to look at the shear stresses that will be applied to the belt and the belt splices. And this can be important in maximizing the service life of both. What I want to do is just run through quickly a number of different lagging types. We'll look at a couple of rubber laggings, and then a number of different ceramic pulley lagging options with different patterns, different tile configurations, and also different thicknesses. We'll look at the performance of each one, and then at the end, we'll summarize and look at which is the best option. All of the following analyses have been done with the same conveyor data. Now, the data you can see is on this table on the left-hand side. We've discussed it in some of the previous courses. One of the interesting things with this set of data that we're going to use for comparing the different laggings is that the T1 to T2 ratio on this particular conveyor is quite high at 3.57. Having a higher T1 to T2 ratio results in greater retraction of the belt as it moves around the pulley. This is the first lagging. It's 12mm diamond rubber, and the analysis shows localized slippage. We can see here that the localized slippage starts at around 175 degrees around the arc of contact, and it results in a total of 37 degrees of slip, or 18% of the wrap angle. Down in the bottom of the table here, these results here, the contact face shear stress, the tread root shear stress, the pulley shell shear stress, and the tile bond shear stress. These are the fatigue results. So long as they're below 100%, it means that the lagging is capable of handling the 5-year service life that's built into the tool. And I want you just to keep an eye on these figures here, which we'll discuss at the end when we do the summary. The first one is the minimum tension, T2 tension to avoid localized slip. And then the one below that is the maximum shear stress between the lagging and the belt. Okay, the next version is 25 mil diamond ceramic. In this case, the lagging's more flexible, and as a result, the localized slippage reduces to 19 degrees or 9% of the arc of contact, which is an improvement over the previous 12 mil. There's no fatigue problems. You can see that none of these figures down the bottom here are exceeding the 100%. Now we'll look at ceramic lagging, and the first option is 12 mil diamond ceramic lagging. This is essentially the same as the previous 12 mil diamond rubber lagging, but with a dimpled tile bonded to each of the large diamonds. The localized slippage is still present, but it's reduced. It's reduced to 14 degrees or 7% of the arc of contact. You can also see here that the fatigue life of the pulley shell lagging interface and the tile bond shear stress have exceeded the limit. That means that lagging would not be expected to last the 5 years service life. Now we'll go to a 25 mil version. Guys, can you put your audios on mute for me? There's some feedback noise coming through.
Let me try that.
Okay, now the 25 mil thick diamond ceramic, the localized localized slippage has reduced. We only have 7 degrees, which is 3% of the arc of contact. The tread route has just gone over the fatigue limit for 5 years, so it's right on the borderline. Let's have a look at 20% ceramic lagging, 12 mil. We have 21 degrees of localized slip, which is 10% of the arc of contact, no fatigue problems. When we go to the 25 mil version, there's no theoretical localized slippage and no fatigue problems. So this is the first of the laggings that we've looked at where we have neither localized slip or any sort of fatigue problems. Interestingly, if you just look at these numbers here, the T2 tension to avoid localized slip is 90 kilonewtons, and the maximum shear stress is 86 kilopascals. When we get to the end and we do the summary, you'll see why that one's significant. So this is a common single row ceramic, 12 mil. We have 40 degrees of localized slip, which is 19% of the arc of contact. We have no fatigue problems. We'll go to the thicker version, which is 25 mil. The localized slippage is reduced to 21 degrees or 10% of the arc of contact. Again, no fatigue problems. The last lagging type that we'll look at is what's called 80% or full ceramic. You can see here we've got slippage starting at about 155 degrees. So we end up with 54 degrees of slip around the arc of contact, or 26%. No fatigue problems. And when we go to the 25 mil version, not surprisingly, the localized slip reduces to 33 degrees, 16% of the arc of contact. So that's all the different lagging types. Let's look at the summary. So what we've got here is the different lagging types that we just looked at across the top with their different ceramic levels of ceramic coverage. We've then got the traction. When you exceed 100% of the traction, that's when you've got slip. This is the amount of slip. Then these 4 lines here relate to the fatigue of the lagging. So we've got the contact face shear stress or fatigue. We've got the tread root, the pulley shell, the tile bond. So there's only one lagging that basically has no localized slippage and is well within the fatigue limits, and that's the 20% 25 mil lagging. And remember earlier on I mentioned about the minimum T2 to prevent slippage and the maximum shear stress. For this lagging, the minimum T2 to prevent slippage and the shear stress are the lowest for all of the laggings that we looked at. And that's important because you're putting the belt and the belt splices under less stress. So what this analysis is enabling us to do is to select a lagging that is not at risk of having localized slip. It's also within the fatigue limits, so we can be confident that we won't get fatigue failure within the 5-year limit in the tool. Then at the same time, the lagging belt interaction is operating at lower levels of tension and stress.